Bob, are we going to run today or
45 minutes. Yeah. Yeah, something going on too.
what?
Yeah, something going on too.
Oh, just my ride.
Oh, okay. Yeah, 45 should be fine. Yeah, yeah. Where are you going anyway?
Oh, so I don't have to walk home.
Oh, okay. I see. Yeah.
Maybe a little bit further.
Where do you live? Far away from here?
Bottom of the beach.
Oh, geez. Okay.
It's not too bad.
It's not too bad.
My range. I definitely have gotten soaked a few times.
That's right. That's right. Yeah. I used to live down there. Second right, second left. There's a big slope. Yeah, yeah. Two blocks behind the Golden State.
How long ago was?
Oh, that was about 7 years ago.
Oh, 7 years.
Quite a long time. Yes.
We'll be going on from the 27th of October. I don't think we have anything paid for several, like, I'll send you an email to let me know. And then, I should be getting an excuse letter from my club advisor.
Just make sure you watch the recording.
Yeah. Thank you.
Yeah, sure. All right, guys. Thank you for coming back to the class on Thursday afternoon. Dreamy weather out there, a little bit sleeping, I guess. So I decided to share with you something exciting, right? At least for me, okay? So this is what I want to show you guys, okay? So here, let me see if I can find my cursor. Here we go. And 12. All right, enough breaking for us. All right, let me just try to close it out. I need to find my cursor again. Not so smart on this computer thing here. All right, where my cursor here? Okay. All right. So what we have learned from this? Well, we're not so smart. We like break bricks to show we have power. Is that only thing you've seen? Oh, come on. Don't be cynical, right? There got to be something nice there, right? So there are two motions, right, to break the brakes. One is the guy is using the forearm, right? It's pretty lean bone on it, meaning it's not a face bone. It's not something flat like a palm or something like that, right? And the second is that he's hitting it pretty fast, isn't it? Very fast impact. But one thing you haven't noticed that all those brakes he broke are supported, isn't it? Simply supported, isn't it? Matter of fact, being like supported. All right. So, what kind of stresses when it hits the brake? Naturally, the bending stresses, but that's not it. The idea of the braking is actually coming from the shear motion. How do I know that? How many of you guys are Kung Fu fans? Martial arts, karate, anybody? Jiu-jitsu, boxing even, cage fighting? That's sort of right. My dad used to be a Kung Fu teacher, right? So the first thing I learned is that watching from Karate Kid and from him is that you have to have a pose, right? Posture when you start fighting, right? So he taught me that you do this, right? Right? So I always wonder why we have to show palm like this, right? Because sometimes we use it to protect ourselves or hit somebody, right? And have you guys ever been hit by somebody who's a palm like this? We call it hand knife like this here, no? Oh, it's very hurtful. My dad even was, right? He said by accident, yeah, sure, right, sure, yeah. You like me so much, right? So what's really going on? Why we use palm? Ancient history, we heard everybody before we invent the guns, of course. Because the pressure, isn't it? It's a smaller area, isn't it? When I exert my small area on my fellow friends, like this, right? Oh, don't worry. No, that's wrong. So the pressure concentrated on the contact surface is extremely high. Is that right? But in addition, what's happening under the contact surface? What I'm trying to do is I'm trying to apply a force that pushing my head this way, essentially, right? Causing a shear stress. And this is a bad gesture, but you can imagine, right? The Japanese samurai move, right? Shear force going on here to sever my tissue. All right. So that means everything is actually weak or vulnerable under shear. Under shear. Right? Just like when you cut anything with a blade, with a kitchen knife. Right? Matter of fact, that is shear stress induced on those materials. Isn't it? So imagine what happens to concrete if you apply shear. It's just like a beam or bridge standing out from my left bank support, right? And have like a 30-ton truck driving from the approach step to the middle span. As the moment I'm passing on the edge of it, what I'm doing is actually what? And karate move, right? So essentially I'm punching the brake and break it. If the truck is over. All right. So we know now shear force, right? As I learned from my karate moves, very, very dangerous to concrete. Okay. So this is the very important part of the concrete design, is the design for shear. Design for shear. Okay. So now let's get to the boring part, shall we? The shear stress. Okay. So here I want to show you some of the distribution of the shear stress, right? So let me open up my slides and I want to start sharing with you that. Okay. Here's my pencils. And here's my screen. Again, I have a hard time to share it. Okay, here we go. Okay, maybe this here. Okay, perfect. All right, so let's talk about shear, right? Shear design. As we just showed you the video, right? If I have a simply supported beam on the left, okay, on the left, And this brick is supported by left and right supports. Okay, knowing that I have a distributed load on the top of the brick or beam in this manner, I'll have both the moment and shear force. And I want to take a look at the middle span here, right? Both moment and shear force at the middle span. All right, why I'm pausing? Hold on 1 second. Okay, can you guys see it? Okay, so now if I show the section AA here, right? Imagine that's where my cut is at, right? That's where you see the middle section that is broken in pieces as the video show, right? So I have a stress distribution, right? Now, if I have the uniform distributed load exerted on top and simply supported conditions on two ends, what kind of moment I have in the middle span? Positive or negative? What kind of moment I have? Positive or negative? Oh boy, I'm in trouble. Thursday afternoon, we're sleepy. Again, positive or negative? Positive, right? Of course, positive, right? So in the positive beam, I look at my section and I start to draw my stress distribution and assume an elastic materials, meaning no cracking in the concrete and no nothing, right? My strain will follow a linear distribution like so. And we know that top is in compression, bottoms will be in tension, right? So compression and tension. All right, so this is from mechanics materials. If I take a look at the section AA again for shear stress, all right, and what is the shear stress equation here? Tau shear stress distributed in the middle section equal to what? And if I say I have a shear force exerted on this section to be V, should be VQ over IB. All right, VQ over IB. Okay, and now if I do this, right, so I have a distributed shear stress like this. Okay, distributed shear stress like this. And the maximum shear stress is going to be in the middle span right here. And that's the maximum shear stress. So in terms of bending, the maximum stress should be either on top in compression or on the bottom in tension. All right, that's how the stress distribution looks like. So here now, if you want to take a look at the stress, right, combine them together, I need to have normal, and that is bending moment M multiplied by distance between anywhere to the neutral axis. So this is Y. And divided by the I moment inertia, and I have shear stress. Then I will have combination of stress state in this beam here. So if I play along and start to look at elements, along this line here, let me clear this out here. And I started seeing that maybe at the bottom, I have one element, and I call it element 3. And in the middle, I have another element called element 1. All right. And then on top, I have another element called element 3. All three elements are having different stress state. All right. Now, what we have learned so far is that assuming we don't care about shear, or we have been focusing on the tensile or compressive stress in the section in terms of fracture bending, right? So if we only focus on this, right? When we bend it, the failure starts from which element? 3, 2, 1. Which one? 3, right? And why is that? Because it has the tensile stress, and concrete is bad for what? It's good for compression, bad for what? Tension, right? So without any reinforcement, concrete will bust first at the bottom. So element 3 will be gone. that right? However, in the video, you have seen not necessarily element 3 will fail first. Is that right? All of sudden, out of nowhere, the break just gone and separated in two pieces. Is that right? And sometimes it actually failed in the middle. Okay. And that is because we never consider the effect of shear stresses so far. So now we have to account for it. You have learned from mechanics materials, right? In mechanics material, we say that if I take this element out, right? If I take this element out, my cursor, I really don't like this. Anyway, so I look at element, let me use a different color here, element 3, for example, right? Okay, and now I magnify my element 3, and I know that it is under tensile stress, isn't it? Under tensile stress. So I know that here I have sigma max tension. Okay. Do I have any shear stress? Do I have any shear stress at element 3? Well, let's take a look, right? Element 3 is at the bottom of the element, so I trace it all the way back to shear diagram, and notice that there's no shear stress in element 3. Very small amount, right? It's on the edge of the diagram and it's almost 0, right? As I move up a little bit, I will see a very tiny amount of shear stress. All right, so let's draw it. So I say that I have some shear maybe, but very small amount, so I can ignore it. I can ignore it. So that means when I have this element failed, right, I need to examine the principal stresses. Do we understand the principal stress definition of that? Anything? Forgot? Galaxy far, far away, long, long ago. What is principal stress? What is principal stress? Anyone? Principal stresses are the stresses that only in what? Tension and compression, right? After you rotate the coordinates to a principal plane, not only have the tensile and compressive stresses, right? So in this case, since I don't have any shear stress, right? I only have the tensile stress. And that naturally is my sigma 1, which is the highest number of the principal stress. And meaning that my failure is going to be a straight crack like that, isn't it? Straight crack like that. Okay, that's what it is, right? Now, if you look at element 3, that's what it is. But element 2 is different. So when I have element 2, I take a look at the element, and there's no tensile stress or compressive stress. Why is that? Because element 2 is sitting right on the neutral axis. All right, it's sitting right on the neutral axis. And on neutral axis, there's no strain. There's no strain. It's pivoting point, no strain, okay? So that means I only have a maximum of shear stress. All right, I only have the maximum shear stress. So when I have sigma 2, I only have a shear stress tau max. Okay, and I don't have any normal stresses. Okay, so for a pure shear stress state, right? And when I convert that into a principal stress, meaning tension and compression only, and we know that I need to rotate that into a 45-degree angle. Okay, 45-degree angle. And then my principal stress will be this direction. All right, and then I will left with a failure direction like this. Okay, right? I break it like that, it will just fail in the middle, right? Now pay attention, folks. For element 3, when I have the failure plane, and assuming that this is in an angle with the direction of principal stress, this is what? 90 degrees, isn't it? But when you rotate to a pure shear stress state, this fellow here, this angle here is what? 45 degrees. Okay, so that's the orientation of the crack. All right, now if I move on to element 1, and let me speed up a little bit for you, and then element 1, it is just like the element 3, but instead I don't have any tensile stress because element 1 is on the top, so I only have the compressive stress. All right, so when I draw my failure diagram for the element 1, I have this nice block here, but I have only the compressive stress. Compressive stress. And when I have compressive stress, the failure is again in the 45 degree, but this goes the other way. Okay, goes the other way, and that is 45 degrees. Okay. You say, Bob, you have lost me. What are you trying to do here? You pick 3 elements from a beam. You did this principal stress, which I forgot long ago, and you draw me this cracks. What do you want, right? What are you trying to do? What I'm trying to do is, if I know all these so-called micro crack orientations under the stress condition, I can draw my cracks on the beam, can I? Can I? I can actually draw the crack patterns on the beam, can I? So that means if I have a beam, simply support it, right? And let me zoom in, right? Show you the beam. So if I have a beam, right, like this, simply support it. And you can go to the civil structure lab, and they have beam tested sometimes, and they have uniformly distributed load here, right? And I can start draw the crack orientations. I can start draw the crack orientations. And how the crack look like? The crack will look like this. One type of crack, okay, will be something like this. And right in the middle, this is in the center span, I have a crack like this. And that is so-called a Fletcher crack. All right, Fletcher crack. Okay, and as I'm getting away from the middle, I start seeing some cracks like this, and like this, okay, and then like this, and I start to see that the more I get away from the middle span, the more likely I see a 45-degree angle. Now I'm talking about this diagonal cracks right here, diagonal cracks right here, diagonal, like that. All right, and now I start to chain them together. I say, look, if I do a line perpendicular to all my crack patterns, I start to see trend. What kind of trend am I seeing, right? What kind of trend am I seeing? I start to see that all these lines indicates that I have something like this. Okay, and these blue lines are called the principal stress trajectory. Okay, here are the blue lines indicate the principal stress trajectory. Okay, meaning that's where the tensile stresses are in this beam, and that's how the crack is formed. Okay, and we call this, in the middle one, 3 is the Fletcher's crack. And as I'm getting away from it, okay, and 2 is so-called shear cracks or diagonal cracks. All right, and now if you notice here in the top here, sometimes you see some micro cracks, right? And these are the crushing crack due to local load. bearing crack, minor cracks. So all we're caring about is this shear crack, diagonal crack. That's what we worry about. So we spent the whole about 10 lectures before today talking about the flexure cracks, how we reinforce that, right? So help me out here. If I put a reinforcement to prevent the number 3 flexure crack, what is the direction of my reinforcement? Is it flat or is it vertical? How we lay our bars, basically? How do we lay our bars? We lay them flat, right? Just like this. Isn't it? That's how I'm going to stitch my flexure cracks. So my question to you is, if I want to reinforce my beam to go against the shear crack, how am I going to put the stirrups or reinforcement in this case? Flat or vertical? Like this? Can I put like this? Can I put like this? Can I put like that? Oh, yes, I can, but that's not efficient. That's not efficient. The nicest way or the best way to put it is what? The best way to put it is something like this, right? If I can provide my bars just perpendicular to the cracks, right? So it'd be something like this. Isn't it? All right, that's how I'm gonna put my bars, but that is hard to fabricate. That's hard to fabricate, isn't it? I can never have an inclined stirrups to fabricate on site. We can, but that's hard to fabricate. So to avoid that, right? To avoid that, we have so-called stirrups to help bridging the cracks. Okay, to help bridging the cracks. Okay, and to make sure they're vertical, I tie another top bar to form the so-called reinforcement cages. Now, we know this, but the quick question is this. If I have my main flexure cracks in the middle, as I'm getting away from the main flexure cracks, I get this diagonal crack, and I'm putting stirrups here. Do I really need these vertical reinforcement in the middle span or not? That means, do I really need this bar or not? Do I need them? Do I need them? I probably don't, isn't it? Why? Because there's no cracks, there is no diagonal crack. The whole purpose of putting vertical reinforcement is to prevent those diagonal cracks, right? So that means if there's no shear, there is no stirrups. Okay, why this is so important? Because say I have a beam, right? I have a beam, and my beam is sustaining, just want to give you an example. My beam is sustaining a concentrated force, concentrated load, okay? And I have support at the 2 ends, and I have every 1/3, I have forces here, forces here. So look at the shear diagram, right? Let's draw the shear diagram together, okay? So here I have, this is P, okay? So here I have shear force of P, isn't it? And I have to have a constant shear force Q. I hit this number here. And when I hit this number here, I become what? 0 shear force, isn't it? Shear diagram 0, right? Then I go on and go on, and I start seeing this shear, right? And it goes here, and that's my shear diagram. Okay, and assuming this is negative, positive, this is negative, and now will be my shear diagram. So my question is, where, if I want to put my vertical stirrups, right? Where am I going to put my stirrups in, vertical reinforcement in? On the sides or in the middle? On the sides or in the middle? It's not a trick question, folks. Where am I going to put my shear? If I only have shear force on 2 ends, right? Where am I going to put the shear? Sides or in the middle? Sides, right? So that will be how dense I put my shear reinforcement here. No shear reinforcement in the web, in the middle. All right. But now, if I take a look at the moment diagram here, if I take a look at the moment diagram here, right? So at two ends, right? And now at this end, I have so-called what? Moment, right? And the moment goes like what? At the beginning, here, do I have any moment? I don't, right? I don't have any moment, right? So here it's gone, 0 moment. And I got to some moment, right? And increase, increase, increase. And then I have a constant moment zone, isn't it? Constant moment zone. And those are the highest moment, right? And then I go down like that, right? So if this is moment diagram. So I put my bars in as well, right? Put my longitudinal bars in as well, right? So then you put bars like this, right? And because here I have a lot of bars, I have a lot of moments. Okay, I will put a lot more reinforcement in the middle rather than the two ends. Okay, so this is to show you that in a general setting, the location of shear reinforcement and location of flexure reinforcement are not the same. Okay, to simplify the design, though, we can make them consistent across the span, but in practical condition, they're not the same. They're not necessarily the same. All right, so we have to study for the shear reinforcement, which means these are the stirrups that we have to study for. Okay. All right, so that is as much as the theoretical side of the shear, right? So let's talk about, where is my document here? How are we going to design for it? Okay, how are we going to design for it? So here, let me see if I can open up my notes. Want to open up this. Give me 1 second, folks. Stop sharing. This is my shared figure notes. Okay, here it is. All right. Go back here, share my screen. All right. Is it seeing anything? No? Okay, here we go. So we now know that we need to design shear differently. So I want to take a deeper look about this failure, right? So here, this detailed design for shear. Okay, detailed design for shear. All right, so we said now, we know most likely I'm going to have cracks at the end of the support like this. And my stirrups most likely is going to run across the crack like that. And not a wiggle line, but vertical stirrups, right? And I have a reinforcement going through here, longitudinal reinforcement. So I'm going to take a quick look at the cross-section cut, right? I say, look, if this is a crack, all right, I'm going to take this part out and zoom in to show that. So I have the left end supported like this, and I have the top beam and arced a little bit and goes in like that. And that is my crack surface. Okay. Now, if I do a free body diagram, this is called free body diagram, right? And then I want to find out the reaction forces. I know that there's supposed to be a compressive forces here, C1 on the top, and there's got to be some shear forces here, VCY, isn't it? Okay. And then on this diagonal crack direction, right, I will now have a shear force here, V. Okay. And let me call it VA. And then I have another piece, which is the counterpart on the right-hand side, right? I want to expose that. And I see that this has an equal and opposite VA to balance the other side of VA. All right. Now, don't forget, I have bars here. And for a moment, don't worry about the vertical stirrups yet. Just say that I already have flexure reinforcement. Bars here, and I cut the bars in the middle, right? Cut the bars in the middle. So here at the cut, I have the tension force T2 from the bar, and I also have a dowel action, right? This is called a dowel action from the bars, like so. Okay, VD. So that's all I have on this enlarged section of a diagonal crack. Okay, now I keep looking at it. I say, look, I know this is called a compression, local compression from the top part, right? And this is a shear force. So VCY is the first shear force I see that it is the shear force at uncracked, isn't it? Shear force on the uncracked concrete. Okay, but I look at VA, we're at this diagonal crack here. Let me go zoom in a little bit more, right? I say, look, if I zoom in here, what I really see in a concrete surface, what I really see in the concrete surface. How many of you guys seen a concrete crack before? A few of you guys, right? Have you finished the concrete surface before? If you did that, okay. Quick question, is it smooth or rough? Rough, right? Would you put your face on it? Probably not, right? Probably not. Why is that? Why it is rough? Because there's cement and also what? Aggregates, right? So here on this interface, instead of smooth surface, I will have these rocks. Isn't it? So these rocks are rubbing against each other to provide that shear resistance, So we call this portion the shear resistance from the aggregates interlocking. Okay, and please remember this because this will be in exam number 2, right? Aggregate interlocking. 2 type of shear force that consist of the whole thing, right? And don't forget, I have the reinforcement to help carry some of the shear force, VD here, okay? So we call this VD here is the shear resistance from Dao action. And this is a contribution from the flexure reinforcement. Okay. Now, with this in mind, the total shear resistance now should equal to VA, aggregate interlocking, VCY, the shear force in the uncracked region, and VD, which is the shear resistance from the Dao reaction. So that is the shear force only exerted from concrete only. Okay, so the idea is to have phi V equal to phi VC plus VS, that this is design shear, right? As we talked about before, greater than or equal to VU. And VS is the stirrups provided resistance. So this is shear from steel. Okay, and this is shear from concrete. Okay, and today what we have talked about is only about the concrete. It's only about concrete. So supposedly how them two work together is I want to draw you the reinforcement cage. In the 3D view, this is how the reinforcement cage looks like. I will have stirrups like this, stirrups like that, like this, like that, right? Like this, like that. Okay, and I have longitudinal reinforcement this way, longitudinal this way, here, here, and that is my cage. And this whole cage will sit inside a concrete section just like this. All right, just like this, inside of this box here. Okay. And the cut or the crack, diagonal crack, will initiate somewhere here and go all the way here. So you see a cut like that. Okay. And if I look at from the side view, and I call it side view, right? Side. So the side view looks like this. Okay. And now if I do the free body diagram, let me cut this and I expose the VS like so. Okay, and that's the top bar, right? And this is the bottom, and this is another stirrups, then a stirrups, and this is the bottom bar like this, right? Okay, so this is VD resistant from the dowel action, and this is VA shear from the aggregates, and this is VCY. Okay, so now the total shear force, like we label here, V should equal VCY plus VD plus VA plus VS. And folks, this one here is the concrete contribution VC. So why bother? Just no number, no equation, no reason. I just provide a reason why bother. Because critical concept is that the shear resistance comes from two sides of it. One from concrete itself, the other from reinforcement. If the concrete itself can provide enough shear, we don't need to put any steel in it. But not necessarily that we have sufficient resistance from the concrete alone. Okay. All right, guys, today's gonna be a short lecture. I'm gonna save most of the mathematical equation on Monday, okay? But I want you to remember this drawings, all right? Here, one. Okay, remember this drawing, and I'll test you in the exam. Remember this drawing, and specifically, remember this drawing, okay? All right, and we will see these three problems in exam number 2 for the shear introduction part. Yes.
Down there at the end, you said VCY, VD, and VA. That is what makes up VC.
Yes. So VC basically equal to them three, right? And there will be three problems. One, multiple choice. I show you the pattern of the shear stirrups. You need to know why this is the pattern. I select the correct patterns per se. The other multiple choice, I ask you, what is the different component shear coming from the concrete side of it? And then last, there's something mathematical calculation we'll talk about on Monday is that when do I need the stirrups and when do I not need stirrups? Okay. All right, well, we have an easy class today, okay? So I see you on Monday, all right?